The freezing point of a substance is defined as the temperature at which its solid phase is in dynamic equilibrium with its liquid phase. At the freezing point, the vapor pressure of the substance in its liquid phase is the same as the vapor pressure of the substance in its solid phase. When a non-volatile solute is added to a solvent, the freezing point of the solution gets lowered. According to Raoult's law, the vapor pressure of a solution containing a non-volatile solute is lower than that of the pure solvent, and therefore it would become equal to that of the solid solvent at a lower temperature. That is why the freezing point of a solvent decreases when a non-volatile solute is added to it. This can also be explained if we plot a graph of the variation of the vapor pressure of a pure solvent and solution as a function of temperature. On cooling, the vapor pressure of the pure solvent decreases along curve AB. At point B, the solid starts appearing. On further cooling, the vapor pressure decreases steeply along BC. This is because solids have lower vapor pressure than liquids. At point B, the liquid phase and the solid phase are in equilibrium and have the same vapor pressure. Therefore, B represents the freezing point Tf0 of the pure solvent. Also, at any given temperature, the vapor pressure of the solution is less than that of the solvent, and curve DE for the solution lies below that of the solvent. Curve DE meets the pure solvent curve at E. Therefore, E represents the freezing point Tf of the solution. As can be seen, Tf is lower than Tf0. Therefore, the difference delta Tf is called the depression in freezing point and can be written as delta Tf is equal to Tf0 minus Tf. The depression in freezing point depends upon the concentration of the solution. For dilute solutions, depression in the freezing point is directly proportional to molality m. Thus, delta Tf is equal to Kf into m, where Kf is known as the freezing point depression constant or molal depression constant or cryoscopic constant. Molal depression constant Kf can be defined as the depression in freezing point when 1 mole of solute is dissolved in 1 kg of solvent. The unit for Kf is Kelvin kilogram per mole. As Kf depends upon the nature of the solvent, its value is different for different solvents. The values of Kf can be calculated from this expression. In this expression, R stands for the gas constant, M1 stands for the molar mass of the solvent. Tf denotes the freezing point of the pure solvent. Remember that all these quantities are in Kelvin. Similarly, delta H fusion represents the enthalpy for the fusion of the solvent. If W2 grams of a solute with molar mass M2 is dissolved in W1 grams of a solvent. Then, molality M of the solution is given by W2 multiplied by 1000 divided by W1 multiplied by M2. Substituting this value of molality in the freezing point depression equation, we get depression in freezing point delta Tf is equal to Kf multiplied by W2 multiplied by 1000 divided by W1 multiplied by M2. For molar mass of the solute, this equation can be written as M2 equal to Kf multiplied by W2 multiplied by 1000 divided by W1 multiplied by delta Tf. Thus, the molar mass of a non-ionic solute can be calculated by studying the depression in freezing point. Let us now solve a numerical problem based on depression in freezing point. Calculate the mass of ascorbic acid, vitamin C, C6H8O6, to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 Kelvin. Kf is equal to 3.9 Kelvin kg per mole. The first step, as usual, is to list the given variables. W1 is equal to 75 grams. Delta Tf is 1.5 Kelvin. Kf is 3.9 Kelvin kg per mole, and the molar mass of ascorbic acid is 176, while W2 needs to be calculated. Substituting the given values in the equation for depression of freezing point of a solvent and solving for W2, we get W2 is equal to 5.077 grams. That is, when 5.077 grams of ascorbic acid is dissolved in 75 grams of acetic acid, it lowers its melting point by 1.5 Kelvin. Let us look at some important applications of depression in freezing point. Running a car in some zero temperatures, even when the radiator is full of water, is possible due to the fact that a depression in the freezing point of water takes place when an appropriate amount of solute ethylene glycol called antifreeze is dissolved in it. Another important application is the use of common salt, that is, sodium chloride or even calcium chloride, to clear the snow on the roads. The addition of these solutes depresses the freezing point of water to such an extent that it cannot freeze at the prevailing temperature, and hence the snow melts off easily.